Everybody, this is Dr. Nigro with the Chem Calculation Screencast. This one's going to focus on Avogadro's law and the ideal gas law. All right, so from the name of Avogadro's law, you can probably anticipate that this law is going to have something to do with moles, and you would be correct. In particular, it looks at the relationship between moles and the space that they occupy, which we are terming volume. All right, now in our formulas, we already know that volume is represented with a V, but you may not remember that when we see moles in formulas, we use a lowercase n. All right, now the relationship between these two variables is a direct relationship, and that makes sense. If you have a container and let's say a balloon, and we've got a certain amount of gas particles in it, if we double the amount of gas particles and don't allow the pressure to change, the only option is to give those particles more space to move around in. So we end up with a formula that looks similar to our other two direct relationship formulas, Charles's law and the Gay-Lussac law, except we have the volume divided by the amount equal to the volume divided by the amount. All right, now, like we saw with our earlier laws, you got to watch your units. Your units need to match. All right, so if you're talking about our volume, we need to have both in liters, both in milliliters. They just need to be the same. For our amount, however, these have to be in moles. All right, so if you're given an amount of a gas and it's in grams, you're going to need to use the molar mass to convert to moles, and then you can use Avogadro's law. All right, now for the other gas law that we're going to talk about today, that's the ideal gas law. And the ideal gas law is a little bit different than the previous laws we've discussed. The previous laws are what I call situational laws, where you have a before and after. You have variables, you change something, you look at what happens to the other variables. The ideal gas law is very different from that. And you can tell just by looking at it. The formula for the ideal gas law is P times V equals N times R times T. And right away, you should notice that it does not look like any of our other laws. There's no ones, there's no twos, so there's no before and after. This gas law lets us look at a particular variable if we know the other three. All right, so we still got the four variables we're used to working with. We have pressure, we have volume, we have amount, and we have temperature. The one new piece is this R. Now this R is called the gas law constant. All right, it comes in a couple different forms, but the one that we are going to use is 0.0821. All right, now the unit for this is a monster. It's a big compound unit, but it's ATMs times liters over moles times Kelvin. And the reason that it's important is that unit sets the units that we have to use for pressure, volume, and temperature. So pressure has to be in atmospheres, volume has to be in liters, and temperature has to be in kelvins. Oh, I forgot pour moles. Let me put moles in there. It also sets that one too. That one must be in moles. All right. So unlike our other gas laws where we just needed units to match, this time we have specific units that we have to use before we can plug into the ideal gas law. All right. Now, like I said, there are other versions of R that have different units in them, but this is the one that we are going to be using for our problems in class. Okay. All right. So let's work a couple problems. All right. This first one, we have a 9.5 liter balloon that contains 5.25 moles of oxygen gas. If an additional 1.25 moles of gas is added, what is the new volume? All right, so if we list out what we know, we have a volume value of 9.5 liters, and along with that, we have an amount of gas at 5.25 moles. The question wants to know what is the new volume if we add in 1.25 moles of gas. So we had 5.25 moles, and now we're going to add 1.25 moles. So our container, our balloon, is now going to contain 6.50 moles of gas. Make sure you do that addition. All right, so we have two volumes, two amounts. This is Avogadro's law, which means that we need to use our formula V1 over N1 equals V2 over N2. All right, now as with our other laws, before we plug anything in, we should check our units. All right, so we've got moles for both amounts. We've got a liter for V1, so our answer will come out in liters, which is fine because there's no requirement for a particular unit in the problem. All right, so now we plug in 9.5 liters over 5.25 moles is equal to our unknown V2 over 6.50 moles. All right, cross multiply, and we find that our new volume should be 11.8 liters. All right, now we're going to check our answer. All right, we saw here that the amount of gas went up. All right, and according to the relationship, which is direct, if we increase the amount of particles within the space, we're going to have to give them more space to move around in. So we would expect the volume to go up as well. And we started at 9.5 liters and ended up at 11.8. So that is, in fact, what happened. All right, so as long as we've done our math right, we should have the correct answer here. All right, let's slide down to this next one. All right, a 6.5 liter balloon contains 2.25 moles of nitrogen gas. Some nitrogen gas escapes, and the balloon has a new volume of 4.25. How many grams of nitrogen escaped? All right, so let's write down what we know. We have a volume value of 6.5 liters, and along with that, an amount of gas of 2.25 moles. We then lost some gas, and we have a new volume of 4.25 liters. So it looks to me the first thing we're going to have to do is figure out how many moles of gas are in that balloon. What we're really trying to get to is what escaped. So we need to know what we have left, and then we can figure out what is missing. All right. So again, Avogadro's law, we've got volumes in moles, and we look, our units for volume look good. They're both liters. We've got moles for N1, so we'll find N2 in moles as well. So V1 over N1 equals V2 over N2. So 6.5 liters divided by 2.25 moles is going to be equal to 4.25 liters divided by our unknown N2. All right, so we cross multiply, solve for N2, and we find that our balloon with a volume of 4.25 contains 1.47 moles of our gas. All right, so this is what remains in that balloon. But the question was to know what escaped. So to find the moles that escaped, I'm going to take the moles I had originally, 2.25, and I'm going to subtract what remains. And the difference there should be what escaped. All right, so the amount of moles that escaped was 0.78 moles of that nitrogen gas. All right, and if it asked for moles of nitrogen that escaped, we'd be done. But it asked for grams, so we had to do one last step. So 0.78 grams, oops, sorry, not grams, 0.78 moles of N2. And we want to convert that to grams. So that's molar mass. So 1 mole of N2 has a mass of 28.02 grams of N2. That's just straight off the periodic table. Each atom of N is 14.01, so I just doubled it. All right, and if we do our multiplication here, we're going to find that 21.8 grams of N2 escaped from our balloon. Okay, so that's an Avogadro's law problem with a couple extra bits there, but this is nothing that you can't handle. All right, so let's move down to number 3. All right, what is the pressure inside of a 45-liter tank that contains 15 moles of oxygen gas at a temperature of 25 degrees Celsius? All right, so this problem is going to be different because I don't have 2 volumes or 2 amounts or 2 pressures. I have a volume, I have moles, I have temperature, and I'm asked for pressure. All right, so when I list out what I know, 45 liters, 15 moles, 25 degrees Celsius, pressure is my unknown, hopefully you'll recognize that this is going to be an ideal gas law problem because we have 1 volume, 1 amount, 1 temperature, and we're asked for the pressure. All right, so that means I need the ideal gas law. P times V equals N times R times T. Now don't forget, R is in units of liters times atmospheres over moles times Kelvin. So that sets all of our units. So we got to check those. Our volume unit's good. Our amount unit is good. We need to convert our temperature from Celsius to Kelvin. So that's going to be 298 Kelvin. And then our pressure unit will come out in atmospheres. All right, so now we plug everything in. Pressure times 45 liters equals 15 moles times 0.0821. Now, everybody always asks me, do I need to write that big unit for R? My answer is I would, because I think it gives you good practice remembering what all your other variables units should be. So I vote yes. All right, and then 298 Kelvin. So we're going to multiply that side, divide by 45, and we should find that our pressure within this container is 8.16 atmospheres. All right, the problem doesn't specify a unit, so I'm just going to leave it in atmospheres. All right, now I'm going to come down to number 4. What volume does a 235-gram sample of helium gas occupy under STP conditions? All right, so we're looking for volume. We've got a mass of 235.5 grams, and the compound is helium. We don't know the volume, and then that seems like that's all we've got, and we don't really have a law that's just mass and volume. So there must be more information here. Oh, there it is, STP. All right, remember, STP is information. It stands for standard temperature and pressure. So standard pressure is 1 atmosphere and standard temperature is 0 degrees Celsius. So just by having STP there, I know these other variables. All right, so again, I've got volume, pressure, and temperature and an amount. It's going to be the ideal gas law. So P times V equals N times R times T. All right, but again, R sets some units for us, so we go back and check. Well, pressure unit's good. I need to convert degrees Celsius to Kelvin, so that's going to be 273 Kelvin, and now that'll work. This gram is not good. I have to have that in moles, so I'm going to take a minute and I'm going to convert into moles. So 1 mole of helium has a molar mass of 4 grams. All right, so I'm going to divide 235.5 by 4, and I'm going to find that I have, wow, I have a lot, 58.9 moles of helium, and that will work with the ideal gas law. All right, so now I go back and plug in. So 1 atmosphere times volume equals 58.9 moles of helium times R, which is 0.0821, which is in atmospheres, liters, moles, Kelvin, and then 273 Kelvin for our temperature. Multiply one side together, then divide by 1 atmosphere, and we're going to find that the volume here is 1,319 liters. All right. Again, for any ideal gas law problem, if you want to check your work, just take what you got for your answer, plug it back in, and make sure the two sides equal each other. If they do, then you're all set. Okay? I hope that was helpful.